Good morning, one and all. Myself, Dr. Bachu, Assistant Professor and HOD of EC Department. Today we are going to deliver about the standard random variable, the density and distributions of exponential, Gaussian and Rayleigh. The last session we discussed about binomial, uniform, random variables. First thing is exponential random variable. Coming to the exponential random variable, a random variable x is said to be exponential if and only if the density function is in the form of alpha into e power minus alpha x for x greater than or equal to 0. Alpha is some constant. Once we know the density function, then corresponding CDF means as fx of x equal to integration of the density function with respect to dx. Now find out the CDF. CDF equal to integral limits integration of the minus limit to x, integral minus limit to the x fx of x. My fx of x value is alpha into e power minus alpha x. Simplify this integration. Integration of the e to the power of minus ax into dx equal to e to the power of minus ax by minus a. So now apply the limits and simplify. Once simplified, we'll get the answer 1 minus e to the power of minus alpha x. This is CDF within the interval x1 x greater than or equal to 0, and x less than case it's 0, and x equal to infinity case its value is 1. Substitute at x equal to infinity, e power infinity plus infinity 0, 1 minus 0 it's 1. So this is my distribution and density of the exponential random variable. You'll see the graphical representation of this exponential is exponentially decaying at x equal to 0 and 0, and from above 0 onwards extends to infinity. Then this value is alpha into e to the power of minus alpha x. Y axis we mentioned density, x axis we mentioned the random variable corresponding assignment values. Similarly, the distribution is when x less than 0 its value is 0, and when x greater than 0 or x greater than or equal to 0 exponentially growing approaches to 1. When x value is tends to infinity, we'll get the value as 1. This is my distribution and density of the exponential random variable. We'll see the applications. First thing is the exponential density is useful in describing the raindrop sizes. In the rain falls, we need to measure the raindrop size. How much size is the raindrop falling. When a large number of rainstorm measurements are made. So in these cases we are using the exponential growing or increasing or decreasing etc. things. And it is also known to approximately describe the fluctuations in the signal strength. Whenever fluctuations occurred in the signal strength received by the radar from the certain types of the aircrafts, that can be estimated, the fluctuations can be estimated or describes the help of the exponentially. Coming to the next topic, the Gaussian random variable, the corresponding Gaussian distribution and densities we'll discuss. We'll draw the plots for these things. A random variable x is said to be the Gaussian if and only if the corresponding density is in the form of 1 by square root of 2 pi sigma square x into e power of the minus of x minus m whole square by 2 sigma square x, where m is called mean value of the random variable capital X and sigma square x is called the variance of the random variable x. This plot is always the bell-shaped form, bell-shaped curve. The x-axis will mention the random variable corresponding assignments, y-axis will mention the density function corresponding values. So this is my Gaussian density, is always the bell-shaped curve, and this is symmetrical about mean value. It's not origin, this is not origin, it's a mean value x equal to m. So we'll estimate the mean value, its average value. So these are the some properties things. Now we'll see the one by one. It is referred to as a normal distribution. The Gaussian or normal is denoted by the n of m comma sigma square x. M is the mean value, sigma square x is the variance of the random variable x. Fx of x is also, we can represent n of 0 comma sigma square x, means here the mean value is 0, is the 0 mean value and unit 0 mean value and variance is sigma square x, that is fx of x equal to 1 by square root of sigma square x, it will be to the power of minus x square by 2 sigma square x. When m equal to 0 and variance is 1, so this is called standard deviation, standard Gaussian, standard normal. It means 0 and variance is 1, that is n of 0 comma 1 is equals to 1 by root 2 5 into e power minus x square by 2 is the density of the random variable with the 0 mean and unity variance, is also called as standardized normal density, standardized Gaussian density, that is n of 0 comma 1, this value is equals to 1 by root of 2 5 into e to the power of minus x square by 2. The Gaussian density function has a maximum value at x equal to mean value only. 1 by root of 2 5 sigma square x at x equal to mean value, at x equal to m substitute, at x equal to m substitute. The power of this exponential is 0, e power minus 0 is 1, so 1 into of this one constant, that is 1 by root of 2 5 sigma square x, where sigma square x is the mean value. This is the maximum value of the Gaussian density when x equal to m. The Gaussian density function is a bell-shaped curve having peak values. Rest definitely it has a peak value, that is the maximum at x equal to mean value, and is always symmetrical about its mean. Symmetrical about its mean. We'll see the graphical representation. So now this is my x-axis is a random variable assignments, y-axis density function of the random variable, the y-axis. Now the real axis values we mentioned, somewhere else we got the mean value of the random variable capital X is equals to small m, its mean value. At this point we'll get the maximum value, so that is 1 by root of 2 5 sigma square x. And this curve is always bell-shaped curve and symmetrical about its mean value, symmetrically it about its mean value. It has equal parts at this point, that point is called symmetrical about the point, it's the mean value, symmetrical about the mean value, not at the origin. So this is a Gaussian density, and this curve the bell-shaped form, that's why this is a Gaussian density. Now we'll see the corresponding distribution. The distribution can be obtained by taking the integration of this density function. I'll get the distribution. The distribution is here, introed all the steps here, directly written the expression, it seems fx of x, the capital F, the distribution of the Gaussian random variable, 1 by root of 2 5 sigma square x, infinite to x, the density function in terms of other variables, e to the power of minus of eta minus d into x square by 2 sigma square x into d eta or d psi. Distribution we mentioned roughly for the sample experiment we mentioned as the Gaussian distribution function values. Now we'll see the Gaussian properties we saw. It has maximum value at x equal to m, and it has a bell-shaped curve, symmetrical about mean value, etc. things. Now we'll go to the Rayleigh density and distribution functions. Rayleigh density function, any density function looks like in the bell-shaped form but not symmetrical about mean values like this. It is a Rayleigh density 2 by b into x minus a into e power of minus of x minus a by 2 into b, or x minus a whole square by 2b, it's not a whole square by b. For x greater than or equal to a, x less than a case it's 0. The distribution can be obtained by taking the integration of then you will get the distribution. The applications of these, it's envelope of the white Gaussian noise passed through the band pass filters, we are using Rayleigh densities. And important analysis in errors in various measurement systems, we are using the Rayleigh density functions. So these are the standard random variable distributions and density functions of the exponential, Gaussian and Rayleigh density functions. Now we covered in the last two sessions, last session and today's session, all the random variable distributions and density functions. Thank you for your patience. Any doubts? can call or contact personally or through mail you can contact. Thank you. Bye.